Hello everybody, it's Dumplet here. Welcome to another item on calculus. Now for today, let us try to solve the following limit. So find the following limit. The limit of e raised to x plus x raised to 2 over x as x approaches infinity. As usual, give this item a try. And if you're done, let us dive into the solution. Now, let's try to have an understanding of this limit. It's an expression in x raised to another expression in terms of x. So let's try to do some analysis. So note how if I analyze each of the expressions separately, as x approaches infinity, this blue expression, e raised to x plus x, that tends toward infinity. So if we substitute x as infinity, it's going to become infinity. So e raised to infinity plus infinity, that's still infinity. So this goes towards infinity. Now for the 2 over x, so the 2 over x here, 2 over a very, very big number, so 2 over infinity, that tends towards 0. So if you want to write like the format of this limit, it's of the form infinity raised to 0. So it's actually an indeterminate form. So since it's an indeterminate form, we can try to use L'Hopital's rule to help us answer this item. Now, the problem is that to apply L'Hopital's rule, we must have a fraction, so a numerator and a denominator, before we can get the derivatives of the numerator and the denominator, and then we will see what we can do with the limit. However, the given expression is like of an exponent, so a base to an exponent, so we must apply one of the well-known tricks in these types of limits. So we start with setting the limit equal to a variable, usually denoted by L. So let's equate this limit to L. And then since we have something raised to an exponent over here, this motivates us to take the natural logarithm, ln. So now taking a natural logarithm of both sides, and we're going to apply the property that if we are taking the natural logarithm of a limit, we can put the limit inside. So this is going to happen. So we have ln L equals the limit of the natural logarithm of the expression as x approaches infinity. Now this part is now very, very nice because we can again apply our properties of logarithms. Since we have an exponent 2 raised to x here, I can put it in the front. So I would have here 2 over x times our expression over here, ln of e raised to x plus x. Now, let's just put it in one fraction so it's easier for us. So 2 ln of e raised to x plus x all over x. So this is easier to work with because everything is one fraction now, and we'll be able to start doing L'Hopital's rule. So we have this. All right, we have the natural logarithm of L is equal to the limit of this fraction over here. Now, since it's already in fraction form, we can start taking the derivative. So let's start with the numerator first. So let's try to take the derivative of the numerator. So we have a factor of 2 here. So actually the 2, we can actually put the 2 in the front. Now let's just deal with the limit ln of e raised to x plus x. Now we will apply the chain rule. We take the derivative of the inside, and this gives us e raised to x plus 1 as the derivative of e raised to x plus x. And then we multiply it by the derivative of the natural logarithm. So it's going to become 1 over whatever is inside the natural logarithm. So it's going to be, so we multiply 1 over the expression e raised to x plus x. So we can put it in one fraction. It's going to be e raised to x plus 1 L over e raised to x plus x. And the derivative of the denominator, well, it's just 1. So this expression is actually equal to, after taking the derivative, this expression, ln e raised to x plus x all over x, taking the derivatives of the numerator and the denominator, we're going to end up with simply this one, because we're just It's the derivative of the blue expression, which is e raised to x plus 1 over e raised to x plus x, and then we're just dividing it by 1 anyway. So we're going to end up with this. All right, after bringing the 2 in the front, so we just have to deal with this limit over here. Now, some of you may have noticed already that this limit approaches 1. Why? Because since we have e raised to x plus 1 all over e raised to x plus x, well, it is well known that an exponential function grows faster than any polynomial function. So since we have the e raised to x here, it's an exponential function, and then we have 2 polynomial functions over here. So we know that as x approaches infinity, both the numerator and the denominator will tend toward the value of e raised to x. So we would expect the answer to be 1. Now, for those of you who do not know that, it's all right, because we can just do L'Hopital's rule over and over again. Since we have e raised to x plus 1 all over e raised to x plus x, if we're going to directly substitute infinity, well, still, it goes towards infinity. So we can apply the following concept here. So we have this thing that will tell us what the value approaches to. So we can, since this is still of the form infinity over infinity, then we take the derivative. So we take the derivative, so it's going to be e raised to x, and then the e raised to x plus x will become e raised to x plus 1. Now this is still of the form infinity over infinity if I substitute x equals infinity. So we can still take the derivative one more time. So the derivative of e raised to x is just e raised to x, and the derivative of e raised to x plus 1 is e raised to x. So after taking the derivative 2 more times, so applying L'Hopital's 2 more times, we would end up that the limit as x approaches infinity is actually just equal to 1. So since we know that this limit over here will evaluate to 1, we know that ln L is just simply equal to 2. So all we have to do now is just get the value of L. Since we have ln to be logarithm of e base L, we just convert it back, and then we just make it base e. So we have L here would be equal to e squared. So this will be our final answer. So hope you guys learned something new today, and I'll see you guys in my next video. Bye bye!